Hi, in today's tutorial we will use the unit architecture to do image segmentation. We will learn how to use the unit architecture to build the model, we will run the train, and then we will take a test image and we will create mask prediction. So let's start. So let's run a short demo and explain what we are going to do in this tutorial today. First of all, we will use this dataset, which is based on car images. As you can see, it's a Carvana image masking challenge. Of course, you don't have to register to the challenge, you just have to download the data. And after you will download all the train and the labels, you will discover that we have images, these car images, and we have another folder that contains all the mask of these images. So basically it's a binary image segmentation, and if we go back to the code, we will basically create a unit model architecture. We will do it step by step. Here is the left side of the unit, and here is the bottleneck, and here's on the right side of the unit shape architecture. And we will do the training process. As you can see here, I will cover all the code step by step, and we will do this binary segmentation process, run the full training, and it will be based on 10 epochs. It should be good enough, although you can run the training for more epochs. And after that we will take a single image. This will be our test image, this car, and we will write two Python programs, one that can predict a mask for a single image. We can run it and you will see the result. Basically it will take this test image and prepare it, load all the saved weights, and as you can see here, this is the result of our test image. This is the original image and this is the predicted mask. And after that we will run it through a test folder. I just created here another this will be our test folder. I just copied some of the images that were not part of the training and copy it to a test folder, and we can when we will code another Python file that run the process through multi images. So it will run through all the folder and do a prediction for the whole process, and after a few seconds you can see this would be the result. As you can see, a perfect result for each car. On the left side you can see the predicted mask on the right side. So let's go to the next step, which is installing the environment, and after that all the coding part. So let's start with the installation part. As you can see, we will use Python 3.11. So let's create a new conda environment. Let's name it unet PyTorch. Of course, you can use your own custom name. And after the creation, we should activate this new conda environment. Next, you have to install a PyTorch. I decided to use in this tutorial the version 2.5.0. First of all, you have to find your CUDA version if you have a GPU card. So we can run this command nbcc in the Anaconda command prompt, and you will discover what is the CUDA version. I have 12.4. After that, you have to go to the PyTorch website and look for the version, the installation command for the relevant version. You can find for CUDA 12.1 and for 11 version. So as I said, I have 12.4, so this is the command for the installation. And after that you have to install two more dependencies, TQDM, so we can see a progress bar during the training, and matplotlib in order to display the result and manipulate the images. So this is the installation parts. Let's download the images. So we will do a segmentation for cars images. So this is the link for the Kaggle website with a specific dataset, and this is the Carvana image masking challenge. And as you can see here, you can download the data from here. There is a train zip, and there is also a test. So you should download this data. As you can see, it's part of a challenge, but you don't need to do the challenge process in order to download the data. It's about 26 gigabyte, all the information. So you should sign for the Kaggle and download the information. I already done it. So if you go to my local machine, you can see I have a folder named Carvana Image Masking Challenge, and it contains the train images. So these are the train images. You can see it's car images, and most important, for each image there is a mask. So the white indicates the object and the black indicates all the rest. So there are a lot of masks for each image. There is a mask with basically it's the name of the image underscore mask and .gif. And there is also a test folder. So basically we will do, after we will train the model, we will do an inference for a specific image and an inference for a full folder. So if we will go back to our code, as always I will leave a link for all the code in the video description. This will be our test image. As I mentioned earlier, I will also run an inference for a folder, not only for a specific image. Great, let's continue to the next step. I forgot to mention one more important thing. After creating the new Conda environment, you have to set up your VS Code to use this new Conda environment. So you should click Ctrl Shift and P. Ctrl Shift and P, and then select Interpreter, and you will see all the environment installed in your local machine. So we need to use the, where is this? It was based on 3.11. This one, UNet PyTorch. You have to choose this one, and now this will be our current environment, the same as here, UNet PyTorch. Great. So let's start coding, and we will build our first Python code, and this will be our unit architecture. And we will start with importing the basics PyTorch and its neural network tools. Next, we will import classes from a new Python file that we will define in the next step. And these classes will deal with double convolution, downsampling, upsampling, and we will explain those classes in the next step. So let's create our new Python file, and we will name it unitparts.py. And once again, we will start with the importing PyTorch, and next we will define the first class. We will name it doubleconv, and this will be a double convolution layer. These blocks perform 2 3x3 convolutions, each followed by a ReLU activation, and it's a super common segmentation task because it's helped to extract rich spatial features while keeping the structure clean. And we'll also create a forward function, this simply passing the input through the convolution block. Next, let's create a downsample block which we'll use in the encoder path of UNet. This combines the double convolution to extract features and max pooling 2D to reduce the spatial dimensions. Once again, I'm not covering the theoretical part, only the practical part. And in this forward method, we will return two things. One is the output of the double convolution. We will reuse that in the skip connection. And the second is the pooled version, which get passed deeper into the network. And we will return it as well. The next class is the upsample, and this is for the decoder path. It starts with upsampling using a transposed convolution, basically reversing the downsampling operation. Then it concatenates this with a corresponding encoder features from the skip connection. And finally, it applies a double convolution to refine the combined features. In the forward method, we first upsample the input, then we concatenate it with the matching feature map from the encoder side along the channel dimension. After that, we apply the double convolution to process the fused features. Now let's go back to our unit code and let's create a unit class. This will be our full unit architecture. We will wrap everything inside a PyTorch NN module class, which lets us create a custom model. Let's start with the init function. And inside the init function, we start with the encoder path for downsample blocks. Each one doubles the feature count while having the spatial dimension. As you can see, 64, 128, and 256. After that, we enter the bottleneck. This is the deepest part of the network. Here we use a double convolution to process the most compressed feature. And now comes the decoder path with 4 upsample blocks. This gradually upsamples the feature back to the original image size. Finally, we output the segmentation map using 1x1 convolution. This reduces the channel to the number of the target classes, 1 channel per class. Next, here is the forward method. This defines the flow of the data through the network. Let's test that the model. Let's test if it's worked as expected. This is just a sanity check. We run when the file is executed directly. First, we try initiating a double convolution blocks and printing its architecture. Great, this is the result. Next, now we create a dummy input image, just random data shaped like a 512 by 512 RGB image. And the batch size is 1, and we are having 3 input RGB channels. We instantiate the full unit model, telling it we have a 3 input channel and a 10 target classes. Let's pass the dummy image through the model to see the output shape, and finally we'll print the output shape. It should match the input resolution but with 10 channels. Great. Now let's build the model for our specific dataset. Let's name the file step number 1, train the model.py. Okay, let's start by importing the core PyTorch module. and we will need it for building and optimizing our model. Let's also import a TQDM. It's a really handy library to show progress bar, great for monitoring and training. Next, we are importing our unit class, and next we will import a new class named myTrain_dataset, and we will generate it in a new Python file. This will help us with loading our car dataset. So this will be our fourth Python file. We will name it myTrain_dataset class. We start with importing the libraries we need working for images and dataset. We will define a global image size of 256. Now we will create our custom dataset class for the training, and this class loads the images and mask from the disk and process them and feed them to our unit model. In the constructor, we pass in the root directory of the dataset. And as you can see, we are loading the list of the images, and next we will load the masks as well. We read and sort all image file paths from the train directory. And next we will do the same, and we do the same for the mask, which are in the train_mask. Great, now for the mask as well. And now we will define the transform pipeline that will apply to both images and mask. First, we resize to a uniform size, in this case 256 by 256, and then convert to tensors. Now the getItem method fetches one image and one mask by index. First, we load the image using PIL library and convert it to RGB. And then we load the corresponding mask and convert it to a grayscale, which is basically a one-channel image. Finally, we will return those images. Let's get back to our code, and let's create a main block for all the rest of the code. Let's define our training hyperparameters. As you can see, we are defining our learning rate. Bits file will be 8. If you have more memory, you can enlarge this value, and let's run it on 10 epochs. The data path variable is where our car dataset is located, and model save path is where we'll save the trained model once training is done. Device is, we will use GPU if it's available, otherwise we will fall back to a CPU. And now we will initiate our dataset using the custom dataset class. And next, let's fix a seed for getting the same results each time. Now we split the dataset into 80% training and 20% validation. And after that, and now we are ready, and now we can prepare the data loader for both training and validation. So this one for the training. Let's define the train dataset and also the bit size. We will also shuffle all the information. And let's define the validation data loader. In this case, the dataset will be the validation dataset, and all the rest should be the same. Now let's initiate our unit model. It takes a 3 input RGB and outputs of a single channel mask for a binary segmentation. We will use AdamW optimizer, and for the loss function we will use a binary cross entropy logits. And next, let's begin the training loop. We will iterate over the number of the epochs. We will set up our model to a training mode, and let's also define another variable of the train loss. We will start with 0 value. And now we will loop over all batches in the training data. And don't forget that the image underscore mask is basically a tuple. It's composed of the image and the corresponding mask. And 0 indicates the image and 1 indicates the mask. So as you can see, we are retrieving the information from each of the batches. Now we will forward pass. The model makes a prediction, zero out gradients before back propagation, calculate the loss between prediction and ground truth, and after that we are accumulating training loss so we can average it later, backwards pass, and then update the weights. After all batches, we will calculate average training loss for the epoch. And after that, now let's evaluate the model on the validation dataset. So we will set up our model to evaluation mode, and let's define a variable for a validation loss, and we will do a similar process for the validation data. And after this process will finish, we will have an average validation loss for the validation data as well. So we have a training loss and a validation loss. And after that, let's print out both training and validation loss after each of the epochs. Once training is complete, we create the output directory if it doesn't exist, and we will save the trained model weights to our local disk. And basically we are done with our training. Let's fix some syntax errors. Should be only one of them. Next, this should be model with, and should set the image to the model. And this is AdamW. And let's run it. Now, as you can see, the process has started. We start training. Let's run it on fast forward. Probably it should take 2 or 3 hours, but let's jump directly to the end of the process. As you can see in the screen, after each of the epochs, the training loss going down. So basically it's a good output. and let's see the result. So the train has finished. First of all, we can monitor the validation lost. Our last epoch, our 10th epoch, you can see that the validation lost was 0.0169, and before that it was higher, and before that it was similar, and before that it was more higher. So basically we can see a very good progress that the validation loss is being reduced after every epoch. And now let's see if our saved model, the weights, if they were stored in this location, the one that we chose. So let's go to our local folder, and as you can see here, these are the weights. So everything was finished successfully, and now we are ready to do some inference. We would like to test our model with one test image, an image of a car, and secondly we will try to do an inference for a full folder, so a folder that contains several images, and we would like to run it to a full folder and see the result. So now let's test our model. Let's run an inference on one single image. So this will be our step number 2. Let's name the file test the model for a single image.py. First of all, let's see our test image. This will be our car test image. It is test_image.py. Let's import all the necessary Python libraries for this code. PyTorch, pil, and let's also import our unit class. And now we have to create another Python file named myTestDataset class, and we will create a class named Carvana test dataset. We will take our train dataset class and we will save it on a similar name. Instead of my train dataset, it will be my test dataset class. And we have to change the train for test, and this will be the test folder, and this will also be our test folder, and we don't need the mask since it's a test images. And now we can continue to the next step. Our test folder contains several test images. Now we will generate two functions. The first function will be for displaying several images with the predicted mask. So it's be like a grid of images. And the second one will be doing an inference for a single image. And in the first Python code we will use on the single image inference, and in the second Python code we will use the function for displaying a grid of images. So let's create both functions, and we will explain each of the Python commands. So let's define our single image inference. It will perform an inference for a single image and display the result. First, we initiate the unit model with the same input and output structure. The same input-output structure that we used during the training. After that, we will load the training weights from our model checkpoints. And of course we will convert it to our device in order to use our GPU. Next we will prepare a transformation pipeline. We will resize the image to 512 by 512 and convert it into a tensor. Now we will load and transform the image, then move it to our selected device. we are loading the image and transform the image. Now the model expects a batch, so we'll unsqueeze to add a batch dimension. We passed the image through the model to get the predicted segmentation mask. Now let's prepare the image for visualization. We will remove the batch dimension and move it back to our CPU. And the next phase, we have to change the channel order. So the channel dimensions needs to be last for plotting. So we will permute it from channel height and width to a height and width and channel. We do the same thing for the prediction mask. And next we have to create a threshold. So at this point we apply a binary threshold to clean up the mask. So everything below 0 become black with the value of 0, and anything above become white, and it will be indicates with the value 1. And now let's plot the results side by side, the original image and the predicted mask. Now let's create a main function for the running process. First of all, we will define the path to the image that we want to test. This image will be part of the code, so you can run it on your local machine as well. So I just copy and paste the path for our test image. Next, we will provide the path for our trained model weights. And finally, we will call our function to run the inference and display the result. So let's run the code for a single image. So run Python. Let's wait a few seconds for the result. Great, let's move it. Now, as you can see, this is the original image and this is the segmentation. You can see the segmented car. There is also a noise here that was segmented as well, but overall, let's say it's very good segmentation. I believe that it will, if we train it for more epochs, it will be more accurate. So let's continue to the next inference, and this is for a batch of images. Now we would like to test our model of a batch of images. So let's create our last Python file. Let's name it step number 3, test the model.multi-images.py. Now copy some car images to a local folder. This will be our test folder. You should do it before creating this Python code. Just test images for our inference of image grid. Now let's define our main function for batch prediction and visualization. First, we will load the trained unit model and move it to the correct device. Next, we will load the saved weights. Now we will load the test dataset using the custom class, the one that we created earlier. Let's store original images and their predicted mask in a two separated list. Now we will loop through each image in the dataset. We will move the image to the selected device and add a batch of dimension, predict the segmentation mask using the model, convert the image back to visualization. Next we will do some processing for the predicted mask, and after that we apply a binary thresholding to the predicted mask, and we will store the processed image and the predicted mask for plotting. Now let's plot all the images and mask in a vertical grid using subplot. And basically for each image we will plot the original image on the left and the predicted mask on the right. So this will be our, let's say, our canvas for displaying the images. And now let's code the loop. We have to ident it, of course. Let's code the loop to run through all the images. And we will display in each of the sides the image and the predicted mask. And of course we don't need axis. So this will be for the image and the next one will be for the mask. And let's use the tight layout to automatically adjust spacing and display the final figure. Now let's create a block to run the prediction. We will set the path to our dataset. This should point to your test image folder. So this is my folder. As you can see, I copied several car images to this test folder. Now we will provide a path to the trained model weights, the one that we trained earlier, and of course add the function that runs the full process. I think I have another syntax error on the my test dataset. After copy and paste, I have to comment this line, and also we don't return the mask, we should delete it as well. Great. So now we are ready to run our Python multi-images prediction, and let's run it. And now it will run through all the images in this folder and extract the mask. So let's wait a few more seconds for the result. Great. As you can see, for each of the test images, we have a mask that was predicted using our model, and as you can see, it's a very good result.